In this video, I will be discussing about the Fundamental Theorem of Calculus, Part 2. So, what is this Fundamental Theorem of Calculus? The second part. If the function small f of x is continuous over the closed interval a to b, and this big F of x is any antiderivative of our small f of x, then the integral from a to b of the small f of x dx is equal to the big F of x evaluated from a to b. So to find the value of the integral, we just substitute to our big F of x the upper limit b here, minus the big F of a, where a is the lower limit in this definite integral. So, the grand statement of the Fundamental Theorem of Calculus paved the way in the calculation of the definite integral. So, to write a proof of this Fundamental Theorem of Calculus, we let P be a set of all x's. So, in symbols we have here x of I, where I is from 0, 1 up to n, and these x's comprise the regular partition of the closed interval a to b. Then we can write our big F of b minus big F of a as big F of our x sub n, the last element of our p, minus the big F of x sub 0, which is the first element in our p. But since our interval from x sub 0 to x sub n is being partitioned regularly, we can write this one as the big F of x sub n minus the big F of our x sub n minus 1. So this is for our first subinterval, plus big F of x sub n minus 1 minus the big F of x sub n minus 2. So this is for our second subinterval. So added to, for the third subinterval, big F of x sub n minus 2 minus the big F of x sub n minus 3, and so on and so forth until you will reach, for the last subinterval, big F of x sub 1 minus the big F of x sub 0 for our last subinterval. Now, we know that our big F is the antiderivative of the small f over the interval from a to b. So, by the mean value theorem, for I from 0 to n, we can always find c sub I for every subinterval, say x sub I minus 1 to x sub I, such that f prime of c sub I is equal to big F of x sub I minus big F of x sub I minus 1 over x sub I minus x sub I minus 1. And if you're going to cross multiply it here, we have this difference of the big F. So big F of x sub I minus the big F of x sub I minus 1 is equal to our big F prime of c sub I times this denominator here, x sub I minus x sub I minus 1. But we know that the derivative of the big F is the small f. So we have big F of x sub I minus big F of x sub I minus 1, which is equal to the small f of c sub I times this subinterval, which can be written as delta x. Now, substituting this statement to our previous equation, to our equation here, which is, say, this is our equation 1, we have our big F of B minus the big F of A, which is, in this equation, is the sum of the differences of the big F over every subinterval. We have this summation of, which is the sum of all differences of the big F over every subinterval, which is this one here. So we write the big F of x sub I minus the big F of x sub I minus 1, where I is from 1 to n. So instead of writing this one, we will write this one here, which is the sum of the small f of c sub I times the subinterval delta x, where I starts from 1 to n. And if we're going to take the limit of both sides of this equation, we have the limit of the big F of B minus the big F of A as n goes to infinity is equal to the limit of this. So we have the limit of the summation of the small f of c sub I times delta x, where I is from 1 to n and n goes to infinity. Now remember that we get this c sub I from every subinterval, say x sub I minus 1 to x sub I. And this is what we represent as the delta x. And the limit of the constant, because this is a constant, is equal to the constant. So this is big F of B minus the big F of A is equal to the sum, the limit of the sum, which is a Riemann sum. So this is from A to B of our small f of x dx. So this is the end of this proof, that the difference of the big F of B to the big F of A is equal to the integral from A to B of the small f of x dx. So this statement paved the way of the calculation of the definite integral, that the definite integral from A to B of small f of x dx is the difference of the antiderivative big F of B and the big F of A. So now let's have this example number 1. What is the definite integral of cosine squared of x over 2 dx from 0 to pi over 2? Now, looking at this integrand, which is a second power of cosine x over 2, we can initially think that we can apply right away the power rule. But if you apply the power rule here, our base is cosine x over 2. And by the chain rule, we need to find the derivative of cosine x over 2, which is negative sign. But we cannot see here a negative sign. So therefore, we cannot directly apply the power rule in integration here. So what we do is to apply an identity for this cosine x over 2, which transforms this second power to the first power. So we have the integral of cosine squared of x over 2 from 0 to pi over 2 dx is equal to the integral of 1 plus cosine x over 2 from 0 to pi over 2 dx. And you can check this one, that this is the identity of the cosine squared of x over 2. And because we have a constant here in the denominator of this fraction, we can pull out this denominator as 1/2 in front of the integral symbol. So this is 1/2 of the integral from 0 to pi over 2 of 1 plus cosine x dx. And we know that the integral of a sum is the sum of its individual integral. So we have 1/2 times the integral of 1, which is x, and the integral of cosine x, which is sine x. And this will be evaluated from 0 to pi over 2. And applying the fundamental theorem of calculus part 2, we need to substitute our upper limit to this antiderivative function of our original function minus the function which is the antiderivative evaluated at the lower limit 0. So we have 1/2 times this one, when you substitute, that is pi over 2 plus the sine of pi over 2. And this whole function will be subtracted by the function evaluated at 0. So we have 0 plus sine of 0. And we know that the sine of pi over 2 is 1. And the sine of 0 is 0. So we have this pi over 2 plus 1 is equal to pi plus 2 over 2 here. And simplifying our answer, we have pi plus 2 all over 4. And this is our answer for this definite integral. Now let's proceed to our example number 2. What is the integral of x minus 1 over the square root of x dx from 1 to 9? So, transforming the square root of x to its equivalent exponential form, we have the integral from 1 to 9 of x minus 1 over the square root of x dx. This is equal to the integral from 1 to 9 of x minus 1 over x to the power 1/2 dx. Now breaking this whole fraction, we have the integral from 1 to 9 of x over x to the power 1/2 minus 1 over x to the power 1/2 dx. Now, simplifying our exponent, we have the integral from 1 to 9 of x to the power 1/2. Because the exponent of x is 1, when subtracted by the exponent of the denominator, which is 1/2, the result is 1/2. And if you move up this exponent of 1/2 in the denominator to the numerator, we have x to the power negative 1/2. So applying the power rule in integration, the integral of x to the power 1/2 is x to the power 3/2 all over 3/2 minus the integral of x to the power negative 1/2 is x to the power 1/2 over 1/2. And this will be evaluated from 1 to 9. So multiplying our numerator by the reciprocal of the denominator, we have 2/3 times x to the power 3/2. And this will be subtracted by 2 over 1, which is the reciprocal of 1/2, times x to the power 1/2. And this will be evaluated from 1 to 9. So, applying the Fundamental Theorem of Calculus Part 2, we need to substitute our upper limit to the antiderivative of our integrand, which is this one here. So we have 2/3 times 9 to the power 3/2. If you substitute our 9 to our x, minus 2 times 9 to the power 1/2. And this is the value when you substitute the upper limit 9 here, minus the 2/3 of 1 to the power 3/2 if you substitute our lower limit 1 to our x, and also minus 2 times 1 to the power 1/2. So we have 2/3, and the square root of 9 is 3, and 3 to the power 3 is 27. We subtract 2 times 3 because the square root of 9 is 3. And then we have minus 2/3 of 1 because the square root of 1 is 1, and 1 cube is 1 also. So plus 2 times 1 because the square root of 1 is 1, and the negative of the negative is positive. So we have 2 times 9 because 27 divided by 3 is 9, minus 6 minus 2/3 plus 2. And this is equal to 18 plus 2. And 18 plus 2 is 20, minus 6 is 14. And 14 minus 2/3 is 40 over 3. So this is the value of our definite integral. Now let's proceed to our example number 3. What is the integral of x cubed times ln x dx from 1 to 2? Now, looking at this integrand, this is a product of an algebraic expression and a logarithmic expression. So therefore, we will apply integration by parts here and say that this is our u and this one is our dv. So let u be equal to ln x and dv be equal to x cubed dx, which is this one here. So finding the differential of u, this is equal to dx over x because the derivative of ln x is 1 over x. And integrating this dv, we have v, which is equal to x to the power of 4 over 4 by the power rule for this x cubed. So instead of writing u, I will write here the integral of u dv because x cubed dx is our dv here, and our ln x is our u. And by the formula of the integration by parts, this is equal to uv minus the integral of v du. And we know that our u is ln x and our v is x to the power 4 over 4 minus the integral of our v, which is again x to the power 4 over 4 du, which is dx over x, which is this one here. And remember, our v is this one. So simplifying our expression here, we have x to the power 4 over 4 times ln x if we write this factor first, and this will be subtracted by x cubed dx over 4. And factoring this constant outside the integral symbol, we have x to the power 4 over 4 times ln x minus 1/4 of the integral of x cubed dx. And we know that the integral of x cubed is x to the fourth over 4. So we have 1/4 times x to the power 4 over 4. And simplifying this one, we have x to the power 4 over 4 times ln x minus x to the power 4 over 16. But remember, we need to evaluate this antiderivative from 1 to 2, which are our limits of our integration. So, substituting our limits of integration, we have 2 here. So, 2 to the power of 4 over 4 ln 2 minus 2 to the power 4 over 16. And this value will be subtracted when you substitute your lower limit here. So we have 1 to the power of 4 over 4 times ln 1 minus 1 to the power of 4 over 16. So we have 4 because 2 to the power 4 is 16 and 16 divided by 4 is 4. So this is multiplied by ln 2 minus 1 because 2 to the power 4 is 16 and 16 divided by 16 is 1 minus 1/4 times ln 1 because 1 to the power of 4 is 1 and 1 divided by 4 is 1/4 and multiplied to ln 1 minus 1 over 16 because this one is 1 over 16. But remember, the negative of the negative is positive here. So applying the properties of logarithm, we can use this 4 here as the exponent of 2. So this is ln of 2 to the power 4 minus ln of 1 to the power 1/4 because this 1/4 can be used as the exponent of 1 here. And remember, we have the minus 1 from here plus 1 over 16. So we have the ln of 16 minus the ln of 1 because 1 to the power 1/4 is still 1. And we have plus negative 16 over 16 if you convert negative 1 to a fraction with a denominator of 16 so that we can add that one to this fraction here. So we have ln of 16 minus 0 because we know that the natural log of 1 is 0 minus 15 over 16. So therefore, our final answer is the natural log of 16 minus the constant 15 over 16. And this is our final answer for this definite integral. Now let's proceed to our example number 4, which is our last example. What is the integral of dx over the square root of 1 plus the square root of x from 0 to 9. Now, looking at this integral, we have something that is like a nested square roots. So, to find the antiderivative of this integrand, we need to use an endogenous substitution, which we call here an algebraic substitution. So suppose we will represent this denominator to some variable, say z. So z is equal to the square root of 1 plus the square root of x. We can solve for x by squaring both sides of this equation. So we have z squared is equal to 1 plus the square root of x. And subtracting both sides of the equation by 1, we have z squared minus 1, which is equal to the square root of x. And squaring both sides of this equation, we have z squared minus 1 quantity raised to the second power is the value of our x. So therefore, our x is the square of z squared minus 1. So we can now find our dx here. So using the power rule, we have 2 times the z squared minus 1 to the first power. And by the chain rule, we need also to find the derivative of the base, which is 2z, because the derivative of z squared is 2z, and the derivative of the constant negative 1 is 0 here. So our dx is equal to 4z times z squared minus 1 dz. So substituting this dx here, which is this one, to our integrand from our x, which is this one, we have the integral of our dx. So instead of writing dx, we will write this one, which is 4z times z squared minus 1 dz. And this denominator is now our z, which is here. And remember, our limits of integration must be transformed to z. So z of 0 to z of 9, because our variable now is not x anymore, but our integrand is in terms of z. So canceling this common factor here, we have the integral of 4 times z squared minus 1 dz from z0 to z9, because there is a change of variable. And factoring out our constant of 4 in front of the integral symbol, we have 4 times the integral of z squared minus 1 dz from z0 to z of 9. Now, applying our knowledge of integration, we have 4 times the integral of z squared, which is z cubed over 3. And the integral of 1 is z. And this will be evaluated from z of 0 to z of 9. And we need to transform our limits of integration because we change our variable. So our z of 9, so substituting our 9 here, so the square root of 9 is 3, and 3 plus 1 is 4, and the square root of 4 is 2. So the z of 9 is 2. And the z of 0, so we will substitute 0 here. So the square root of 0 is 0, and added to 1 is 1, and the square root of 1 is 1. So z of 0 is 1. Now, substituting our limits of integration, we have 2 cubed over 3 minus 2. And this result will be subtracted when you substitute our lower limit of integration, which is 1. So this is 1 cubed over 3 minus 1. So we have 4 times 8 over 3, because 2 cubed is 8. And this will be subtracted by 2 minus 1/3, because 1 cubed is 1. So this is 1/3. And this will be added to 1 because the negative of the negative is 1. So we have 4 times 8/3 minus 1/3, which is 7/3, minus 1, because minus 2 plus 1 is minus 1. And this is equal to 4 times 7/3 minus 3/3. And 7/3 minus 3/3 is 4/3, Therefore, our answer is 16/3. And this is our final answer for this definite integral here. And that's it. If you learned something today, please check out my channel for more videos like this and click subscribe. Click the notification bell below so you'll get notified whenever I'll be posting a new video. Don't forget to like this video to show your support. And always remember to math your way up. Thank you.